Hello and welcome to Func Prog Sweden. My name is Magnus Sedlacek and I'm part of organizing Func Prog Sweden meetup, and also warm welcome back if this is not your first meetup with us. Today we'll have 3 presentations. We'll have type-safe, message-driven, distributed, a whirlwind tour of Akka by Johan Andrén. Second presentation is Developer Ergonomics with VS Code, Cluser Script by Peter Strömberg. And third presentation is Functional Programming Primer for Java by Deepu K. Sasidarian. I hope I pronounced your name right. In the end, I'll do a little bit the schedule for the rest of the season and a summary. First up, we would like to thank our video sponsor, Adabeat. Adabeat is a small IT consultancy company based in Stockholm, where most of the developers have a background in functional programming. If you want to know more about Adabeat, check them out on adabeat.com or in social media. If you have questions during the presentation, please use the YouTube chat and I will read out the questions to them. Or if you have feedback, just push it out in the YouTube chat. If you don't want to use the YouTube chat, just go to the meetup. You have the possibility to also comment under the actual meetup. So just post your question there or feedback, and I will push it to the audience and to the presenters. With that said, let's start. First presentation, type-safe, message-driven, distributed, a whirlwind tour of Akka by Johan Andrén. Warm welcome, Johan.
Thanks for having me.
Yes, you're warm welcome. I'm super thrilled. We actually finally got a Scala guy here. I've been actually looking for a Scala guy for, I don't know, a year. Where are you people? Now Johan is here. Thank you very much and welcome. So I'll hand over the HDMI and hope it works. Maybe. Yay.
All right. So let's get started. I work as a developer in the core Akka team at a company called Lightbend, primarily known as the Scala company, but also maybe now more kind of moving into focusing on Akka and also serverless stuff. So for this talk, I have kind of chosen a good sampling of what is in the Akka project and the umbrella projects. So we're going to cover a bit of actor basics, the idea of actors and how those look in Akka, and then we're going to have an overview of components for building distributed systems based on actors. But in the toolkit is a gazillion of stuff, and there's a lot of ground that we won't be covering in this talk. So, at the core of Akka is the actor model, maybe known to you from other languages. So there is like the most known language that has actors is Erlang, but there's also a smaller, maybe less successful language called Pony. And at some point, like 10, 11 years ago, the founder of Akka, Jonas Bonnier, thought there needs to be an actor framework toolkit for the JVM, because this is a really good idea. And the whole idea revolves around avoiding concurrency primitives to do concurrency and distribution. And instead of doing nitty-gritty little synchronized stuff and using primitives that is hard to get right every time, we abstract this to a model that makes it so that you get it right every time without a large effort. So each actor has an inbox, and the only way to communicate with it is by sending it messages through this inbox. And the surrounding system, the actor system that manages the actor and the actor lifecycle, will make sure that the actor processes a single message at a time. So you get a single-threaded illusion for interacting with state and stuff like that. So when an actor gets a message, it can do three things. It can mutate state, so it can have its own state, but it can also have children and also mutate like its life cycle, so it can, for example, stop itself. It can send messages to other actors. So a single actor isn't very interesting. They always come in systems, so you have many of them, very likely. And then the third thing an actor can do when it receives a message, when it processes a message, is to change its behavior for the next message that comes in. So this makes it possible to build state machines with actors based on the incoming messages. I'm not going to do a lot of code in this presentation. If that's what you came for, I can promise that the next speaker will do some live coding. So please stay put and bear with me. But I will show some code. So I will start with a very simple actor with the typed actor APIs that we introduced in Scala 2. In Akka 2.6. So to build an actor, you start with defining a protocol. Usually the protocol is more of an ADT, or you have a marker interface and then a flat hierarchy of actual messages. So this protocol type determines what kind of message that an actor can receive and make sure that you get a compile error if you try to send something that isn't handled by the actor. So we have an older API, the classic actors API, where you don't have this kind of guarantees, and this is something that took quite a while to kind of formulate how we wanted this to work and how to actually implement it. So in this case, we have a very silly example. We have a single message protocol with a hello class that contains a single string, the who field. When we define the behavior for the actor, it will have a type parameter that identifies this protocol. So this is part of how we guarantee that you can only send this type of message to this actor, the kind of message that it knows how to handle. Then there's a bunch of behavior factories based on this behaviors object. So in this case, the most simple one is the receive message. It will simply get handed an incoming message. And we get to do some form of processing. In this case, we do a print line, standard out print. And then we return like a special marker factory thing called same, which means stay with this same behavior for the next message. So this actor, however many messages you send to it, it will always keep having this behavior. To actually run this in an application, we need a main function, a main method, and to start an actor system. So an actor doesn't run kind of on its own. It's not an object that you create yourself, but it's managed by this actor system. And once we have started it, the system becomes the reference to kind of the root behavior, the root actor of it. So we can send it messages. As you see, we send like 2 hello messages with the tell method, the bang operator. And these are asynchronous, so the execution of the main thread will immediately kind of pass by these 2, probably before the actor actually gets to process the messages and do the print lines. But the system will keep the application alive since it's a managed thing until this root actor stops itself. All right, let's do something more interesting. Add some state. So we have the same protocol, but instead of making like a static behavior, we make a method that captures some form of state and returns a behavior. So in this case, we keep a counter. The first time when we create this actor, when we start it, we call this with counter 0 to return a behavior where the count is 0. And then for every message we receive, instead of returning same like we did before, we return a new behavior where we have increased the count with 1. So this kind of looks like recursion, but it isn't, because the control is handed back to the actor system between messages. So it doesn't actually call itself. It returns a new behavior with the increased count value. So it's a kind of functional style way to represent state. It's also possible to do a more class object-oriented way, but this is very neat for a lot of cases. And also, of course, if your preference is functional programming, this is perhaps a better fit than the class-based. So this only kind of showed how to receive messages, but let's talk a bit about how actors can interact with each other. So what we saw in the main method, that was a fire and forget using the bang or the tell method. So I will immediately send off a message, and then the calling thread will continue with its logic. And all kind of messaging in actors, in Akka, will be asynchronous like this. There is no way to kind of block on a call to an actor or kind of stop the current thread from doing stuff. And that's like at its very core in how things are designed with Akka. So another very common one is request response. So this is kind of very close to calling a function or a method, but it is asynchronous. So you fire a message off, and at some point in the future, you get a response. So you kind of react on the response rather than that you block a thread and wait for it. And then the third would be that you, rather than you see it as a request response interaction, you actually send several responses. So you can call that a subscription. So an actor tells another actor, you can send me messages of this type. And he will do it like when something happens or at a repeated kind of interval or something. Based on these like 3 different ways of interacting, you can build a lot of stuff. And I'm not sure if there is any more ways of interacting that is really important or needs to be kind of upfront kind of talked about. So let's look at an example where we actually do a request response style interaction. So in this case, we have not only like the string in this hello message, but we also have a reply to actor ref. So an actor ref is the kind of reference to a running actor. And the type parameter here, just like with behavior that we saw before, limits what kind of messages we can send to it. So in this case, when the actor gets this hello message, it can only reply with a string. So when we get this message, we capture this reply to, and we send a string back. And except for that, it's identical to the previous example where we just kind of increase the counter by 1. And to show like the other side, how a requestee could look in this case, we have a factor method for this that accepts an actor ref to say hello to. But our own behavior for this second actor behavior is string. So this is how we know that we can only get string messages to this actor. And that also means that the reference to the running actor itself will be an actor ref string, which is exactly what we had kind of designed in this little protocol. So when this actor starts up, we send a hello message and we pass it a reference to ourselves. And then at some later point, we get a response message from the other actor. So this shows how we react on this response rather than send or wait or block for getting it. And in this case, instead of returning same that we did before or a new behavior with some increased counter, we kind of change the life cycle of the actor by returning behaviors.stopped to stop the actor. All right, so this was kind of the low detail code kind of stuff. Now I'm gonna kind of migrate into distributed systems and a more kind of overviewy part of this talk. So a distributed system is basically when you have written an application and you want to run it, kind of distribute it over several computers or several JVMs on the same computer, but kind of several running processes that take part in the same application. So usually this is interesting because you want fault tolerance. So you want to know that if the hardware of one machine breaks down and doesn't work anymore. You want your system to be able to handle requests still. But it can also be about your problem outgrowing a single computer. So if you have a problem that doesn't fit into the memory of a single computer, you want to kind of scale that out over several computers to be able to handle more load. There's some other kind of use cases as well, but I think those are kind of the two primary use cases. Maybe also if you run out of CPU and need to scale that out, like more CPU than you can fit in one machine. And it also lets you kind of do this with commodity hardware, so you can have like cheaper servers instead of buying a really expensive one with all the resources to run the application as one. But of course, it comes at a cost. So there's a good quote from Leslie Lamport, which is a researcher in distributed systems. A distributed system is one which the failure of a computer you didn't even know existed can render your own computer unusable. So hopefully this is something you want to avoid, but there is something to it. So what we saw in these previous samples was me starting several actors in one actor system. A really cool thing about this is that it lends itself really well to distributing, because messages between systems is essentially how computers talk across networks through packets and messages. And it also kind of deals with the fact that you're not in the same memory space. So with actors, you have already modeled your messages, your interaction as immutable messages. There is no way that a mutation of this message can change something on the sending side. And also very closely to the idea of it is that messages can be lost. So if the other actor has crashed when you send it, you might not know that, and that message is lost. But across a network, then the risk is much, much higher that messages will be lost, because networks are in their core nature not very reliable. So we can model this with messages and do resending. And also one thing that kind of gets lost if you model this kind of stuff with RPC is that not only requests can be lost, but a request can succeed and then the response gets lost. So you have actually succeeded in doing some operation on the other side, but you don't know because you didn't get the response. But this will still look like a networking error that your RPC call failed. So with messages, this is easier to kind of model retrying around and doing idempotent kind of actions based on a message and retrying it. Another pretty cool thing with the actor model for distributed systems is that you don't have to do a request response chain that follows the same path. So if you have an actor on one node that sends a message to an actor on a different node that in turn sends a message to an actor on a third node, the third actor can respond directly to the actor on the first node. It doesn't have to go through the intermediate actor. And of course, like this messaging, as I showed in the interaction examples, it's not limited to request response. You can do a lot of different patterns where both sides can start an interaction, or you can have many messages back, and you can have streams of messages and stuff like that. All right. So to do this, an Akka actor system can take part of one Akka cluster, which is a peer-to-peer based remoting kind of thing where nodes know of all the other nodes in the cluster. So to form a cluster, there is a programmatic way to do it, to send a join message to an existing cluster, or the node itself to kind of start a new cluster, or you can do it through config. And those two are maybe interesting mostly if you are in a very kind of static set of nodes, but nowadays I guess most people will be in a more cloudy, dynamic kind of environment, which makes forming a cluster a bit trickier through these programmatic or config-based solutions. So for those, there is a whole kind of little umbrella subsystem thingy called Akka Management and Cluster Bootstrap, which uses for example, Kubernetes API to discover other nodes and form a cluster. So once a node is in the cluster, it will start gossiping with the other nodes. So the state of the cluster, which nodes are in it and their life cycle state, is an eventually consistent data structure that on each node at some point will reach the same state. So when a node joins a cluster, the other nodes will start gossiping to their neighbors or their friends about that there is a new node in the cluster, and eventually all of the nodes will know of all the nodes in the cluster. The same goes for like leaving a cluster. There's a failure detector to detect if a node is no longer reachable. So this can be used partly to kind of divert work to other nodes. And it is also possible to use it to get rid of the node if it turns out that it's not only temporarily unreachable. So this can be a bit tricky to know for sure with distributed systems. So was this just a network connection that we lost for a while? Or was it actually this remote node that crashed that isn't there anymore? So in the case of things going back to green again, so let's say that was someone spilled coffee into the router, and now you put all the cables into your replacement router. The cluster will know that this node became reachable again. You can kind of use it for traffic. But it could also be that this node is permanently out of the cluster. You will never see it again. And for this, there's a component called the split brain resolver, which can kind of detect and remove those nodes from the cluster. This is also maybe more important in a dynamic cloudy environment where you scale in and out dynamically and things like that. So a tricky problem is partitions or split brain. That is, let's say your cluster lost connectivity like between a part of the cluster. So for example, a giant scissor attack. So with the kind of basic setting for Akka, this means that the nodes on both sides they stay up until this kind of problem is solved. And the things that ran on that side of the cluster can still continue running, accepting requests, dealing with things. But usually when you end up with this kind of problem, you would like to kind of shut one side down and continue with just like the other side to kind of rebalance and become one cluster again. Because a lot of things needs consistency, needs to be able to talk to each other. And that will not work as long as you have this kind of a partition. So, yeah, there was nothing more there, sorry. Surprising animations. So the user API of this is very kind of limited. It's basically a way to know about the node itself that I'm in right now, the code that I'm running in an actor, can see, am I in the cluster? Have I joined the cluster? Have I left the cluster? What is my address? Stuff like that. And I can also do programmatic kind of operations to join the cluster or to leave the cluster again. And I can also do programmatic downing of other nodes. Not very often that is super useful, but you can do that. And I can also listen for events to the cluster. So when the cluster topology changes, when new nodes come in, I can get an event to an actor. So I can tell it to do stuff once there are more nodes or less nodes, stuff like that. Okay, before I start with the actual kind of cluster components, this is a new thing in the typed APIs called the Receptionist. So the Receptionist is the way to kind of look up other actors based on a name and a type. So you define like a key that contains a name and a type, and then actors that provide a specific service can register using this key. And actors that need someone that provide this service, they can either do like a single lookup and get the list of actors that fulfill this contract right now, or they can do a subscription to get updates every time the set of register actors changes. And why I say this isn't like really one of the cluster components is that it also works in a non-clustered actor system. So you can write something that relies on this receptionist and run it in a single actor system without a cluster in your unit tests or stuff like that. And then it will work clustered once you're actually running a cluster. And there are some other components that are based on this receptionist that we will see later, but also routing, which basically looks like an actor F, but does some kind of round robin or random selection of actors that you actually send a message to kind of distribute work. So it looks like this. On every node, there's a receptionist, which is an actor in itself, but it comes pre-packaged with Akka. It's always started when you start the actor system. One actor, in this case, our hello actor, it can register itself with a key. And this is gossip to the other node, so it's also just like the cluster states, it's an eventually consistent data structure, the registry, the set of registered services. And then on some other node or on the same node, I can subscribe to updates for this key. And every time the set of registered services change, I get a listing. And I can then use this listing to send a message to one of them or all of them. For the case where I just want to send to one of them, we have these routers that I mentioned earlier, and it kind of abstracts over the need to keep track of this listing. And instead, you can just kind of say, this is the key. Send messages to the available actors with this key, like one of them at any time. All right, so let's go with the cluster tools. So one quite important thing for the cluster tools is that there is a scale from strong consistency to availability. So if the angry scissors are out there again, cutting the cable, like a component can either always be available and be able to handle requests on both these nodes, even though they can't communicate with each other, or it can be strongly consistent, and that means it cannot handle any requests until it can talk to the other node, basically. So for each of these components, I'm gonna like say about-ish where it is on this scale. So let's start with cluster sharding. This is maybe the most used clustered component with Akka. If I look at like our customers and the user base of Akka, this is what most people use, together with event sourcing, the event-sourced actor APIs, which require a single writer per ID. And cluster sharding provides guarantees around exactly that. So instead of sending a message to a specific actor, the routing is based on an ID which is in the message. So it has a way to extract this ID from the message, and it makes sure that there is only one actor with a given ID in the entire cluster at a given time. So when actually running, it will look something like this. It's a hierarchy. So each node has a shard region, and each shard region can have a bunch of shards, and each shard can have a bunch of sharded actors. And when I send a message through this shard region with an ID, it will get routed to a node where the right shard and actor is living. And if it isn't running yet, it will be started. If the cluster topology changes and we remove that node where it used to live, it will be started on a new node. If we scale the cluster out, add more nodes to handle more load, for example, it will rebalance the existing shards across the cluster, so to kind of make use of all the nodes in the cluster. The incoming message can come from any node on the cluster, so you don't have to kind of align this. You can actually put a load balancer in front and let it send requests to any node in the cluster. And this sharding routing will handle sending it to the right node from where it is kind of turned from HTTP into actor messages, for example, or gRPC or whatever. So this one is sort of strongly consistent. It guarantees that there is only one at a time of a specific entity. So if there is a partition and unreachable nodes, it cannot start new shards. It cannot rebalance. But those actors that were already alive can be interacted with. But I still decided to kind of put the arrow closer to strong consistency than always available. But it's not quite the truth. All right, let's look at the next component, distributed data. So distributed data is a component based on CRDTs, conflict-free replicated data types, which is a way to allow a data structure to be updated on any node concurrently. And those changes will then kind of be gossiped in the cluster, and the data structures on each node will eventually reach the same kind of state. It's not possible to use for kind of any data structure. It has some very special requirements. So the operations needs to be commutative. You need to be able to do them in any order. So for example, addition, if you do addition with a number, doesn't matter which order you put the numbers, it will always be the same result. It is also important that grouping operations doesn't matter. You will always end up with the same result. So this is also true for addition. And it also needs to be monotonic. We cannot kind of undo stuff, but there's some sneaky tricks around that. So you can build your own data structures that kind of live up to these requirements, but there's a few built-in ones. So there's a counter that only increases. You can add to it on any node. So let's say likes on a YouTube video. You could accept a like on any node in the cluster, and eventually the counter on each node will reach the same state based on how many likes you have gotten. There's also a PN counter, which kind of handles both adding and removing to this number by keeping two counters. How many additions were made and how many subtractions were made, and then we can kind of calculate the sum based on those two. Same goes for sets. We can have sets that we only add to, which is fine, or we can do OR sets, which are basically sets where we keep track of what was added and what was removed. And then some kind of more complicated structures based on that, like maps. And also like a very specific last rider wins map, which isn't that hard to build yourself without this. And then we also have like flags and registries, like flags where you can have a Boolean that you can only toggle once. So in action, you will have a replicator actor running on each node. You can ask any of these replicators the current value of a key. And you can subscribe to changes of one of these data structures to get updates every time it changes. And then you can update it on any node. And those changes will reach all nodes in the cluster. So this is different from sharding. This will always be available. Even if you would partition the cluster into one partition per node that couldn't talk to the rest of the cluster and have it like that for an hour, you could still accept writes, and you could still see like the local state. And then when you kind of fix the partition so that the nodes can talk, they will all kind of arrive at the same end state. Right, next component is distributed pub/sub. So this is based on top of the receptionist. So it's very close to what we already have seen. It allows you to define a topic and then have subscribers, one or more subscribers, or 0 or more subscribers on each node of the cluster. And it will deduplicate message sending. So if you publish a message and there are more than one subscriber on a specific node, the message will only be sent to it once. Just like with the other tools, you can subscribe to or you have to subscribe to the topic to get updates, to get messages. And then when you send messages to the topic, it will arrive at all the subscribers known at that time. So this is another one of the always available kind. Like the registry of subscribers is somewhat eventually consistent because it uses this receptionist. But it also means that if you have a partition and there is a send on one side of the partition, it will never reach the other side because that is just how messages work. You cannot send messages across partitions because there is no network connectivity. Right. Next one, cluster singleton. So this is something to avoid, but there are almost always scenarios where you want to have something that there is only one of for the entire cluster. So cluster singleton guarantees this. It will give you tools to send messages. It will manage like which node an actor runs on, which will always be the oldest node in the cluster. And then it has a proxy which allows you to send messages to it without knowing yourself which is the oldest node. So we send a message through the proxy and it will pass that to the singleton actor. If that node is crashed, removed from the cluster, the singleton actor will then be started on the new oldest node in the cluster. But while it is unreachable, it will not be available for a while. So this is like you're introducing a single point of failure for sure. So this is for certain strongly consistent, and you won't be able to interact with it, and it won't be able to start a new one unless a cluster node where it lived was removed. Sometimes you want to do kind of that thing with the singleton, but you want a specific set number of these. So a very common use case for this would be consumers for Kafka. You want to run 10 consumers for Kafka across your cluster. If you scale your cluster down to 5 nodes, you want 2 consumers per node. If you scale it up to 10 nodes, you want 1 consumer per node. So this component is pre-sized. You can't change that across like a deployment. If you want to change it, you need to stop the cluster and start a new one with a new number. And it doesn't really have an API to interact with these processes. That doesn't mean that that is impossible, but there is no kind of proxy or anything like that, like with the other tools. But they can still kind of use the receptionist, register themselves, or use the pub sub topic or something like that to receive messages. And this is actually built on top of cluster sharding, so it's a composition of another component. This is also strongly consistent, but not always available. So it will, if you change the cluster topology, it will stop that thing for a while and start it on a new node potentially. And if a node is unreachable, it might not be running. You don't know until you have removed it from the cluster. Right, that was the last component. So in some scenarios, a single cluster isn't enough. You might want redundancy to be able to tolerate the whole data center crashing or losing power, I don't know. Or you might also want to kind of co-locate actors for a user group with them geographically to kind of get better response times. Or just balance the load over a ton of servers, make that easier maybe than to run a single cluster. So for this we have support for multi-DC. And each DC is like a logical grouping, so it might be an actual DC or a availability zone or something like that, but it might also be just a logical kind of logical grouping of nodes in your cluster, in your application. So each of these clusters will basically be like a separate cluster, but they can interact in between with messages. So actors in one data center can send messages to actors in a different one. So in the cluster tools, if you run sharding, it will be like one set of sharding per data center. Will guarantee one instance of an entity, an actor in the same data center, but not across data centers. Distributed data and pub sub will work across them, I think. Cluster singleton will also be per data center, so it will be 3 if you have 3 data centers, or you will actually decide to run it in just one of them and interact with that from the other data centers. A quite recent addition is replicated event sourcing, which is a combination of eventually consistent data structures and event-sourced data structures, where you can actually have multiple separate instances with their own data store running at the same time. So for this, you could have a persistent, an actor that persists its state with event sourcing, but runs one instance per data center that are eventually consistent. So if one data center goes down, you can keep writing to the same actor in a different data center, and then when the data center comes up again, it will kind of catch up after a while. Yeah, so this is kind of the end of it. All of these components are have a lot of documentation. We have put a lot of effort into documenting it in our reference documentation, so you can find that through the akka.io site. On top of that, discussion forums, discuss.akka.io. We also have something called the platform guide, which is a more kind of high-level description of how you write distributed microservices with this and how you put it into production on AWS or GCP, the Amazon or the Google clouds. And as I mentioned earlier, we're working on this Akka serverless thing, so keep your eyes open for what is coming there, because it will be pretty cool, I think. Right. Thanks for listening.
Thank you very much. Thanks for your presentation. Very interesting. I haven't received any questions so far, but I have some questions on my own.
Right.
First, I would like to thank your presentation. I think it was really good on the presenting like eventually consistent, how it works, what it works. I love the thing with the scissor attack. I never heard of that before.
It's a well-known technical term.
Yes. How come you started up using Scala and then went into Akka?
So like Java has seen a ton of changes the last 4 or 5 years, since maybe even since Oracle took over from Sun. It started getting things rolling again. But at that point in time, 5-10 years ago, it was kind of stale, and you didn't see a lot of kind of interesting language improvements that are first now they are arriving in the language, right? With the Java 16, 17. And it was like a whole new world that kind of opened up to me. So at university, I studied Haskell and all these things, and I never kind of saw the practical application. But then all of a sudden, having access to a language that could do that within reason on the JVM, that I could use at actual companies to build actual software, and not only as an interest or a hobby, work with a team to build something concrete. That was really interesting. And I think also, like, as a language having one leg in the industry and one leg in the academic world, that made it also very different from a lot of other Angular languages, which would be either. So Java would be in the industry only and not caring about new ideas about type systems or stuff like that. And languages like Haskell would be like only in the academic world and super interesting, but so far from being something that you could introduce in your workplace.
Yes. Where did Akka come up with the idea? Did it take it from Erlang, the message?
Yeah, so I mean...
Was it any other particular or any other language? Or?
So I mean, the actor model as an idea, of course, like the academic ideas from the 70s, maybe even. But there was certainly a lot of inspiration from Erlang.
Yeah. Interesting. And then you shared a lot of sources in the end. We'll share it under the film or the YouTube later, so everyone can find them. And we'll also share your contact stuff, so they can find you if they want to ask you questions or want to know more.
Sounds good.
Yeah, or want to work with you and are super interested in getting to know Akka more.
Yeah.
Yeah. Thanks again, Johan.
Thank you.